I'll start with the introduction. And so the inclusion process was first introduced as a some dual process of a certain diffusion named the Brownian momentum process in the 2007 paper by Giardina, Perchen, and Reddick. And this inclusion process is a natural counterpart of the much more well-known exclusion process, right? So the main difference is that for the exclusion process, the particles are repulsive, so that particles tend to spread out. But in the inclusion process, the alternatively, particles tend to attract each other, so that particles tend to assemble rather than spread out. So, yeah. So because of this reason, because of this attractive behavior, so people expect that the inclusion process will exhibit a phenomenon of condensation, and this is roughly a phenomenon that most of the particles tend to accumulate in a single site. So this is a phenomenon which is also happening in, for example, supercritical or critical zero-range processes, which is also a very well-known particle system. And so because the inclusion process is compared to these previous two systems, inclusion process is a very new system. So there are very many ongoing works on this dynamics, and many open questions are still to be resolved. So, for example, there was a contribution session last year at the Bernoulli IMS 10th World Congress, chaired by Christian Giardina. And also last month, there was a small webinar of inclusion process and sticky Brownian motions, which was organized by Simone Floriani. So I will briefly define the process. So first, I write the Hn as the coherent space, which is the collection of eta, so that the whole number of particles are n, where n is a large number. And here we'll fix S as a finite collection of sites, so that then the Hn becomes just a finite set, so we don't have to worry about some technical issues about like convergence or something. So Hn is our configuration space, and on Hn we define a interacting particle system eta and t, which is defined by the infinitesimal generator Ln, which acts on functions f on Hn by the following formula in the display. So first we have the term Rxy here. So Rxy is just a underlying random environment on the finite set S. And for simplicity, we will assume that R is irreducible. And so here we have the configuration eta to the xy. So eta to the xy is a configuration obtained from eta by moving one particle from site x to site y. So that eta to the xy has one less particle on x and one more particle on y compared to eta. And so if you read this generator, so given a configuration eta, so the generation rate for a particle to jump from x to y is given by this following term, eta x dn plus eta y, and dn here is a constant which depends on n, and this controls the diffusivity of the dynamics. So in the following sense, so we can rewrite the rate into these following two terms. So the first term is dn multiplied by eta x. So this is just so particles on eta x perform a diffusive random walk according to the rate r. And the second term is eta x eta y. So so the point is that for the particles on x, they tend to jump quicker to those y which have bigger eta y. So particles tend to attract each other. So the particles tend to move quickly to the more occupied sites. So this second term features the attractive behavior of the system. And in this talk, we will assume that the constant dn is sufficiently small, so that in that sense, the attractive behavior becomes to dominate the diffusive behavior, right? So so this is a formal definition of condensation. So the inclusion process exhibits the phenomenon of condensation if this following limit holds. So here mu(n) is the unique stationary distribution of this particle system, and this is unique because the system is irreducible and we have a finite Markov chain. So this is unique. And so the set here is that we collect such eta such that there exists one site x, so that all the particles of eta is staying on the site x. So these are actually very small subset of Hn, but still, if the small subset occupies most of the stationary distribution, then we call this a phenomenon of condensation. And so because if this condensation holds, then And most of the time, starting from any configuration, during the process, particles will tend to pile up in a single site. Yeah. So a quick remark is that this is actually a rather strong definition of condensation, and you can find some other concepts of various definitions of condensation in the following paper, and one of the authors is, of course, Paul Cleveland, who is sitting right there. So you can check this paper. Yeah, so we have defined condensation, and yeah, so after the condensate is formed, we still have a small diffusive behavior characterized by the constant dn, right? So because of course it takes a long time because the dynamics have a very attractive behavior, but eventually because of the small dn, the diffusivity forces the condensate to break up eventually, and this needs a longer time scale because of the smallness of dn. So I'll call this time scale by theta n. And after this condensate is dismantled, yeah, again, it will be very easy to form another condensate, right? Because of the attractivity. So the disassembled particles will form another condensate on maybe a different site. It can make, of course, on the same site, but it can make a condensate on the different site. So summarizing this in a somewhat energetic point of view. So we start from a condensate, which can be seen as locally stable state, and at some point it breaks up. So when it breaks up, it will be some kind of unstable state, and it can make a condensate again. So it's just again locally stable. So in this point of view, we can characterize these movements of the condensate as a metastable transitions between the sites of condensate. So this is what we call metastability in the interacting particle system. Another thing I want to mention is that there exists a case that I said that the metastable transition between some sites and condensate on each site can move to the other site, condensation on other sites, right? So, but it can happen that there might exist some unconnected sites. So few of the pairs of S are not cannot go each other in this first time scale theta n. So in that case, but because the dynamics is actually irreducible, so we can expect that there exists a longer time scale than theta n, so that in that bigger time scale, it is eventually we can move from that site to another site, which was impossible in the first time scale theta n. So we will get to this point with an example. So this was rigorously mathematically formulated in the paper by Bertrand and Claudia Landin, who is also sitting right here. So you can see this for a mathematical definition. Yeah, so I also forgot. So this is the difference between this one and the metastability in the zero range process, where for the zero range process, there is only one time scale. So in the time scale, the condensate can move among all the sites in the system, but yeah, for the inclusion process, we have a hierarchy structure so that we need multiple time scales. Okay, so this is the introduction, and so as I said, I'll focus on the reversible inclusion process from now on. Okay, so the first proposition deals with the stationary measure mu(n). So the most good point about reversible inclusion process is that we have a nice explicit product type formula for the measure mu(n). So so we will define as small n as the invariant measure on S with respect to the underlying random walk R. Then if we denote by large M as the maximum of this value measure M, then we have the following product type formula for mu(n). So so this is very nice because we can, so in the limit as n goes to infinity, we can have a very sharp estimate on the stationary distribution itself. So it really helps a lot in analyzing condensation and metastability. So yeah, so we will now we will define S max as the collection of sites X in S, which attains the maximum measure M. So for sites in S max, the Mx is actually equal to large M. Okay, and we need another quick notation. So for a site X in S, so we'll define a metastable value ENX, which is actually a singleton in this model. So this is the singleton where the one configuration in the set is the eta such that eta x is n and the number leftovers are 0, right? So this is the singleton set in EX, and moreover, if A is a certain subset of S, then we'll define E and A as just a union of all ENX for X in A. So now we can present a condensation result for the reversible process. So this is a proposition in a paper by Alessandra Bianchi, Sander Domers, and Christian Giardina. So in the reversible case, then we have that for all site X in the S max, we have that the asymptotic stationary measure becomes a positive value, which is 1 over the cardinality of S max. So that then automatically we can see that if we union all these sets, then we have that the stationary measure for the En S max becomes asymptotically 1. So you can see that this set is very small compared to the whole space Hn, because this set has only cardinality is the same as S max, right? But it has all the basically all the measures of mu n. Okay, so now I'm going to move on to the metastable transition of condensates, and this is just a technical. So this is a trace process, and I won't go into details for this, and I'll just explain that the trace process is just so for the trace process we fix a subset, certain subset G, which seems very important for the Hn, and we just kill the clock when we are out of the set G, and we resume the clock if we return to G. So in that case, if we trace the original process with the notations like here, eta n to the GT, this is a new process which is now on process G. Now the process is on G rather than the whole Hn, and this becomes indeed a strong Markov process. So I'll skip the details. And yeah, so we need a projection operator, which is written by here, psi sub 1n. This is just we just for each metastable value eta, which is a sole element in ENX, we just move eta to the subscript x, maybe superscript there. So we just take the label out of each value. So this is a projection operator, and using these two concepts, we define a model chain which I write by x and t. This is a chain on S max as the following. So we start from the original chain eta n. We take a trace process on the set En S max, and this is En S max contains essentially all the stationary measure mu n because of the previous proposition. So this is very natural, and we project it to the set S max so that Xn is a process on the small set S max. Okay, so so then we can present the first theorem. This is also by Bianchi, Domers, and Giardina. So for the reversible case, we can see that the time scale becomes 1 over dn here. So I'll write theta sub n1. 1 is because this is the first time scale. So if we define the first time scale by 1 over dn, then if we accelerate the modal process xn by this time scale, then this converges to a very simple Markov chain on S max. I'll call this a X first. And this is a Markov chain which whose transition rate is just R. R was the original random walk transition rate. So yeah, this is a very remarkable fact. And so I remarked that convergence is of the weak convergence on the scored topology. And yeah, the main tool that we use is the Markov approach, also invented by Bertrand and Landy about 10 years ago. Yeah, so at this point, I think it will be very helpful to look at a example. So the left picture is a site and an underlying system of R. So the blue dots are the sites in S, and if a arrow is from X to Y, it means that Rxy is bigger than Ryx. And if there's a dotted line between X and Y, it means that Rxy is actually equal to Ryx, which is bigger than 0. So and if there's nothing, then it's just base all 0. So in this model, if we color by red the sets of S max, which is the maximal imperative measure sites, and if we color by yellow the other sites, then okay. So the previous first theorem indicates that if we accelerate the process by a factor 1 over dn, then we have a metastable transition cell of condensate. So for example, if to start where if the initial configuration was a condensate in this site, then this condensate in the accelerated timescale will move back and forth between these two sites. If we start from here, then we can move along these three sites. And like, for example, if we start here, this is isolated, right? So there is no red point, so the condensate just stays here in the time scale 1 over dn. So yeah, so the important remark here is that the first limiting dynamics, which is x first, may not be irreducible. So this is even though R on whole S was irreducible, we can have that the R restricted on S max is not irreducible. So this suggests to seek for a next time scale. So we'll go to the second time scale. So now we'll decompose the red dots S max into the irreducible components with respect to the limiting dynamics. So if we return to this picture, yeah, so in this case, we will have exactly 4 irreducible components, right? So for general, we will say that we have kappa number of components, which I write by S1 to the paraphase 2 and and S kappa to the paraphase 2. So, and moreover, we need some different projection this time because, yeah, so in the next time scale, we need to indistinguish all the sites which are actually connected in the first time scale. So the second projection sends each metastable values to a smaller set, which is 1 to kappa, so that we just read the label from each representative. This is a projection to a smaller set, and we define now. So we define as usual the y and t is the original, traced, and projected. Okay, so then I can give the next theorem. So this was published last year. So for the reversal case, the second time scale becomes like the following. So the time scale is n over dn square, which is strictly bigger than 1 over dn because n goes to infinity and dn converges to 0. So if yn is accelerated by this time scale n over dn square, then this accelerated process converges to a Markov chain. So this is actually not simple anymore. It's very hard to calculate, but so yeah. Nevertheless, this chain lives in a simple set 1 to kappa, and this transition rate is given by the following. So don't worry about the constant Rij. And I'll just remark that so Rij is a positive constant which can be infinite. So I and j in the second time scale are connected if and only if the component Si and component Sj are exactly 2 distance apart. So I'll explain this in the following the continued example. So this was the first time scale, and the second time scale indicates that we have 4 irreducible components, right? So S1, S2, S3, and S4, and then we have a second time scale metastable transition between S1 and S2 because they are exactly 2 Rex distance parts, and S3 and S4 because they are 2 Rex distance parts. But here we have no other pairs of components which are exactly 2 because so that only movements between these and these are possible in the second time scale. Yeah, so the important second remark here is that x second may not still be reducible, right? So yeah, so this is how many times?
You should.
May I use 30 seconds more?
Yeah, yes. Let us say 2 minutes. 2 minutes.
Okay. Yeah, so I will finish it quickly. So yeah, so we want to seek for the next time scale, which is the third time scale, but unfortunately this is not done at this point, and this is still a conjecture. So we conjecture that the third time scale is n square over dn cube, and moreover we think that this is the last time scale, which means that in this third time scale all the sites will be connected. So in this continued example, the S1 and S2, which is colored blue, will be one component, and S3 and S4 will be one component, green, and we'll have a transition between green and blue. Okay, so this is the and so this is my list of references. Yeah, and thank you very much for listening.
So is there any question? Yeah. Yes, so Federico.
Hi, thanks. I wanted to ask you, you had these 2 different conditions on the dn decay.
Yeah.
Between first and second time scales.
Yeah, you're right.
What do you expect? I mean, are they sharp? These 2 conditions? Do you expect something between can happen? Or
yeah. So, I think that the optimal condition is for the first time scale, which was dn log n converges to 0. That condition appears a lot in this inclusion process in other conditions, right? So the condition here, which is dn n square log n square converges to 0, is, I think it is very purely technical, and I think the same results should hold in the minimal condition dn log n converge to 0. Yeah. But this is, I think, it's purely a technical condition.
Is there any other question?
And
Chiara?
Yeah.
have you thought of also in the asymmetric inclusion? Do you think you can get similar result because you have reversibility and I think also condensation?
You mean asymmetric?
Yeah.
Yeah. So actually, that was the next with. Yeah. So this is the third section. This includes the most general underlying random walk, so that it includes all the asymmetric walks. But yeah, I didn't have time to explain it. Yeah. So
Thanks.
yeah, maybe we can talk about it later.
Anyway, the slides will be uploaded on the website. So
Yeah,
we will see this part.
Great.
And Claudio, maybe you have a question?
You have an idea of the time for condensation. If you start from a uniform, homogeneous configuration, how long it takes for to form the condensate?
You mean nucleation, maybe?
Yes.
Yeah. Actually, this research is somewhat independent of the nucleation regime. I expect it will be very quick because starting from any configuration, because of the constant dn, so the movement between the occupied sites are very quick. So there's no dn term between the movements of the occupied sites. So I think the nucleation time is, yeah, I think maybe it will be also 1 over dn, because if they form some kind of 3 or 4 clusters, then we have to wait a time of approximately 1 over dn to collide them to make a one condensation. So maybe I think nucleation time is 1 over dn. But yeah, I haven't think about it very much. Thank you.
Okay, thanks. So we don't have further time for questions.